So I think I've got it figured out, at least at the intuition level, and I'm maybe not 100% happy, because I think there's a couple of things that there's a couple of those concepts that basically are derived purely from the mathematics. So they're pretty hard for me to explain intuitively, but I'm going to give it a try. So the first thing is I've been doing some research on what this whole thing with the Hamiltonians is, and because it's really getting too much into the physics, but at the end of the day, it's just I think most of the confusion around this is both. It's actually the fact that they're trying to. So this is depicted here um, in a really generic way, which is something that has to be done in order to prove that is everything correct mathematically, but it doesn't help to understand the concept. So I had two big blanks in my mind. So one was what the Hamiltonian thing is, and the other one is sort of the generic concept of a gradient. And so for the Hamiltonian, really all Hamiltonian is just a and probably I'm saying this wrong, right? So don't blame me for this, but at an intuitive level, it's just a way to express it's a way to express the energy of a system and the way the system evolves with time. Sort of, it's a function of the energy of a system through time, roughly. At the end of the day, it's just another way to express what a gate does. A gate is just changing the energy levels, maybe roughly, really, really intuitively speaking, right? So at the physics level. And so you can of course represent gates with different Hamiltonians, but what they're saying here at the end of the day, when you take a look at the practicality of the example and take a look at this part here, and how they implement that, is just so they're basically saying the Hamiltonian should be a Hamiltonian of, so that depends on how you implement the discriminator. And I guess that's why they want to keep it generic here. But if we remember and if we stick to the fact that the discriminator is implemented like this means rotations on X, rotations in Z, etc. I think basically at the intuition level, you can say that the Hamiltonians are the same, right? Because at the end of that's basically what I could come up with in terms of based on what I've been reading. So which kind of makes sense. Because at the end of the day, and then that brings me to what the gradients are. So at the end of the day, let me open maybe the quantum experience. So I'll just try to. So this is where we left, and this is totally wrong. So that's the first thing that I want to say. This is totally wrong. But if we just trash this for a second, and this, it's not wrong, but in the sense that it just doesn't, you can't build it this way, because really what they are saying in the paper and the way this is described in generic terms is, and what confused me a lot is this J here at the bottom, right? So and really all what this means is, if you take a look at the way this is being described here in terms of the derivative and all this stuff, it's like you're calculating the derivative of the entire function, but in relation to one particular parameter, so the theta underscore j. So the basic idea is, let me show you what I mean by this. I keep forgetting here. So I'm gonna start a new clean one, not this. Let's clear this one out. We'll get to this later. So so basically what we were doing here is we're building the one of the layers like that. And if you haven't watched the other videos, check out the other videos of the same playlist, and exactly. And then there's like a control rotation, exactly. So this was basically a layer. So in each of those elements, right, and you can put that into a box, but each of those elements has a parameter, right? So when you when you want to calculate the derivative, you have to do this in relation to each of the parameters. Because at the end of the day, and that brings me to this really awesome page here from David Kopchik, where he explains the concept of quantum circuit learning. I'm not going to go through that right now, but you can go ahead and read that. It's super interesting, because basically what it says is, at the end of the day, how do you want to learn? How do you want to learn and adapt a quantum circuit? Well, you want to basically test out different variants of it and then figure out which one is the best, right? So what if we tweak this parameter here? What if we tweak this parameter there? But this is just one way to do that. You could also just, say, what if I remove this gate here? What if I add this gate here? And by calculating, it's at the end of the day the same concept like you have with the sort of basic derivative concept that of a function, where you basically measure 2 points of the function that are really close to each other and then take a look at the difference. And this is basically what you can see here. This is what David is kind of outlining here, which is basically you calculate, so your parameter is this theta, and then you add something, and then you remove something, so you kind of have a really small difference in terms of the parameter, and then basically check what's the difference and what you like, and whether that's something that you want to then use to modify the theta or not. So this is roughly intuitively it's nothing else. It just keep bubbling up levels of intuition. It's nothing else than just how a human learns, right? It's trial and error. So you try something, doesn't work. Next time you're going to try a little harder, or you're going to try a little smoother, you're going to try a little more on the right, or a little bit more on the left. So this is not, it's not magic. It's just intuitively that's what's happening here. So the trick though is that what the paper is trying to do is trying to do this within the same circuit. So it's trying to come up with a different strategy to do that. So what they basically say is, this is nothing else than, so this first gate is whatever else comes. So let's put ourselves in the context of, let's say, this here, right? This parameter here. So this was an example. I think that's really nice. This parameter here. So and now we want to calculate the derivative in relation to that parameter here. So the way they say that is basically you've got, so set up an ancilla qubit here, and you've got a Hadamard. And we're going to explain you now why this is important. What they're saying is, what they're trying to measure here is, by adding this as a control, is they're calculating what would happen. So what's the circuit with this gate or without this gate, right? So it's not just a tweak in the parameter, but it's saying, what if this gate was not there? So this Hamiltonian in this case is the same, right? So it's the same gate. So you put in the same gate here, right? But it's not the same gate. It has to be controlled. It has to be controlled. So it's a controlled rotation, right? But it has to have the same parameter, right? So it has to have the same parameter. So that's why the Hadamard is useful, because the Hadamard is going to basically calculate for us those two possibilities at the same time. So it's going to tell us, okay, what if it's 0? Then this is not going to happen. So this is the equivalent of we keep the gate. And if it's 1, then this rotation is going to happen, which and sorry, it's not the same parameter, but it should be like that, right? So it should be the inverse, so to say. Because in this case, the Hamiltonian of that, yeah, okay, I guess so, right? But that's roughly the idea. And so we have this first part here, and then the rest of the circuit stays the same. So nothing else happens. Now, what is all this P and W? I've been looking at this for a long time, and the only explanation that I can come up that it's sort of that I'm okay with, in terms of the W, for example, is this is just part of the way the derivative is. So if you take a look at the mathematics, and sadly that I haven't figured out another way to do that, but maybe I will find the same concept in the future. Maybe I'll explore that a little bit more in the future, and then it's like, aha. But I basically, because the gates are in a general form expressed like this, when you do the derivative, then this complex, this I, comes down. And so basically they define a gate, right? That basically what it does is, So if you see this is 1 divided by the square root of 2, and then you've got this here. It's basically actually adding that to your computation, to your calculation. Is adding that I that you get because of you're doing the derivative. But there's no, I can't figure out I can figure out a more intuitive explanation out of that. So this is just pure, it's coming from the fact that our general expression, or the general expression that the authors of the paper use, has that in the mathematics, right? And so the way you would do that here, and I don't want to dive into the details, is probably with the U3 gate. So the U3 gate basically gives you 3 parameters. With this gate, you can implement whatever you like, every gate. So you've got 3 parameters, and it's described in here. So this is the formula. So this is how the matrix looks like. So you only have to solve for that. So if what you want to build is this, so remember that term goes into each of the components of the matrix. You only have to try to solve those equations. So you have to basically try to figure out what are your, close that. What are your, your theta is 1 parameter, your lambda, and then the phi, I think it's called a phi. So you have to figure out those 3 based on that. And then if you do that, you can implement the U3 the way that it's supposed to be implemented. Yeah, so but this is there just because of that, and the Hadamard obviously is kind of there to undo this, right? And now there's another operation in the circuit, which is the control. So let me scroll down to here. So that's another thing where, so there's a control Z. That's kind of the practical example. There's a control Z in here. This control Z, it's something that I also can't explain at an intuitive level as of now, but it pops up here, right? So and in a more generic form, because the paper is structured first a generic concept, then the concrete concept. It's this P here, which I think intuitively, my intuition tells me that is your measurement basis. That is, yeah. So that could be a Y or control Y or control X if we would be measuring another basis, I think, but I'm not entirely sure. But that could be enough to believe this is what's really happening, right? So and now you almost got it all. So to compute the gradient of that, the thing is, this other concept here as well. So this X gate here. Which basically also what they say is that this is important because in the case that the generator chooses one or the other, we want to tweak the theta positively or negatively. So this X gate is also something that has to be conditionally there. I mean, in the sense that here say it's the identity when the discriminator is using the real data, and it's a not when it's using generated data. So let's, as just to be it as an example, let's put an X here. And so really, and this is basically it, right? So I've added now, so I have a separate circuit for just that specific one here. And so we would need to do the same. So remember, this is what we are calculating the gradient of, so to say. So, and or in respect to that parameter, because each parameter is different, you would have to do that for each of the other components of your discriminator, which I'm not going to do this because it's just, I can't do this all together here, but that's roughly the idea. And how this is then interpreted, basically, exactly. I have to get used to the shortcuts, maybe a bit more of this tool. So, okay, so now you've got this fancy stuff. So we are going to do, we're going to measure that, and I'm going to save that. And I'm going to run that. Maybe I should just change the name. This is sort of like gradient example. But remember, this is a specific type of gradient calculation, because it's actually, if you read through David's paper, David's post explains you how you calculate those gradients and then how you do that sort of on the classical way outside of the quantum processor. This happens all inside the quantum computer. So because it's kind of embedded in the circuit, not just the calculation, but the interpretation. Because what we want to do is what the paper says here is we want to measure. Where is it? Where is it? Where is it? I lost it. Exactly. So we want to measure the probability of seeing a 0 minus the probability of seeing a 1. And this is exactly what you're going to modify your parameter with. So if you go up here, this is basically what you're gonna update the parameters based on this. So let's see if that runs. I hope that runs. I'm curious to see the results, because I've been playing with this concept a little bit before, but I was not sure whether this was really the. So we've got here the pending completed. Let's see. So you've got like a fancy decomposition of all this stuff. Yeah. So you see. So you've got basically 14% and 85%. So 0.14 and 0.85. So what you would do is you would do this minus this, and this is the exact delta that you would apply to the parameter. For of your theta, of the one that you've sort of to that theta here. Now you would do that until you kind of get equal probabilities of zeros and ones, which means that you've reached your limit of learning. So this is roughly the idea. That's probably been a huge dump of information right now. Again, I don't feel 100% happy with the results of this playlist of building the quantum GAN, because I haven't really been able to explain everything at an intuition level. And but I mean, maybe I'll come back to this. I don't know. Maybe I'll come across the same concept later on. But this is, this is basically, I think, good enough, because. So specifically bothers me the control Z and the U3. This is basically coming from. It's basically coming from the derivative formula and or expression. And I think here what we're doing is basically by having a control Z, we're tweaking the phase of our ancilla qubit up here based on the outcome of the whole thing, right? So this exact operation is what makes for the difference between the probabilities, kind of, because this is applied or not applied based on Hadamard, and then I mean, it's probably the combination of both that make up for these differences. Yeah, so I hope it's been understandable enough. If this hasn't been understandable enough, bear with it. This is super. I didn't expect that building a quantum GAN would open up such an amount of different topics. And I'm happy on one side that this happened this way, but I'm sad on the other side because I feel that I've been drifting a bit away from what's the main purpose of the channel. But at least I've learned a lot of things, and I hope that you have as well, especially when it comes to the Hamiltonians, when it comes to the whole concept of the gradient, when it comes to how to implement, fancy weird things like this one here. Well, especially, things like that. That's been a really interesting insight as well. How do you build a generic model? So I'm really, really, really happy from that perspective, and I hope that you guys enjoyed the series as well. And if you have any more questions, just leave them in the comments down below, and stay tuned for more content on building up intuition for quantum computing.